This is the last book. This is like the last lesson I'll ever teach right now.
Wait, what?
It's true. It's true.
You timed this like really well.
Did I?
Yeah, last year was pretty far in.
Well, and then we have lots of review stuff, right? So, I mean, I'll probably stand up here and talk again. But, okay, so any issues on this warm-up or on the homework? Any of the concepts we talked about yesterday? It's messy, but you know how to find dy dx in polar coordinates. Ew. And we know how to plug stuff in, and we also know how to find the length of a curve. Yay. The tricky part we learned is actually figuring out what the bounds are, and it is not always obvious. And maybe it takes intuition about the curve or investigation with your calculator or what have you. Another question one might ask is, when it comes to length of curve, is could you find the length of the pedal up here or something, right? And you'd have to maybe figure out what the bounds, where this is 0, and what those, when we're here and when we're here again. That would take a lot of investigation maybe to think through what those values would be, but you can do it, right? So the other thing we should say too, especially moving into today, we're going to be doing area inside of polar curves like these, okay? Is both in the length of a curve discussion and the slope too, really. And especially with area, we're gonna really, there's lots of symmetry happening here, right? So like if someone asks you what's the area inside this total curve, if we could calculate the area of this thing and the area of this pedal, then we could just double that and we'd have that, right? So let's do that as often as possible and use symmetry, because there's tons of symmetry in these polar curves. So use it anytime you can to get to your advantage, Okay. Alright. So recall that the length of a circular arc is r theta when theta is in radians. I say recall, but maybe you don't remember that. You remember that arc length formula? In particular, remember that r theta is the length of the arc even when theta is 2 pi, right? So in general, by arc I mean like an arc inside of a circle, right? I'm asking what is the length of this arc? And the answer is, it's the angle theta in radians times the radius, which is one of the huge advantages of using radians, because this formula in particular is so simple. Just r theta. Yay, that's so great, that's so wonderful. In particular, if our inside angle here is 2 pi, right, we get the whole circle. So it would just be 2 pi r, which is the formula for the circumference, which you know and love, right? So this is in general though, this is forget the circumference formula, this is like the general arc length formula for any arc, of any length. Okay, so that's good. That gives us the length of this highlighted segment I emboldened there. And then, as usual in calculus, we want to consider things that are straight and linear in a way. So how do we compute the area inside of a polar curve? Well, we're going to divide it up into pieces of pi that are actually like this, but when they're really small, are basically triangles. And the area of a triangle is 1/2 base times height. So this dashed purple line is just for any function that we're going to be playing with. This is going to be our r value. And this here, the base, will be r times d theta. Why? Why r times d theta? Well, we just talked about it up top, right? It's approximately the arc length when we're dealing with very, 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 very small arcs here, right? It's going to be r times theta. Well, theta is very small theta. We're going to be dealing with the d theta here. Yes? So what is the arc length for a d theta? Well, it's still r d theta. So I know this should be kind of curved, right? But when it's small, it's basically not curved. It's basically linear, right? Isn't that our trick? So we've got one play in our playbook in calculus. Pretend it's linear. So then what is the area of this thing using the area formula? Well, it's, we'll call the area dA, how about? It's 1/2 base times height. So we get, in the end, 1/2 r squared d theta, right? That is the area of one sliver of area on a polar graph. And then say we have an actual curve in polar coordinates, right? And say this is the pole down here. This is some curve in polar coordinates. we want to compute the area inside this curve, not just one sliver, but add them all up. That's our next trick in calculus, is once we have little tiny approximation, we add it all up. From, how about alpha to beta, right? We want to add up a whole bunch of infinitely small slivers, all of which look like can be at least approximated in the small case by this picture up here, right? So in general, when you slap an integral on both sides of this equation right here, you get our result down below. So the area inside of a polar curve is maybe not what you would first expect. It's a little complicated, but here's where it comes from. It's 1/2 times the integral from our starting angle to our ending angle, r squared d theta, where again r is that whole function in polar coordinates, whatever the function that gives this purple line here is, this purple curve. Does that make sense? So the derivation is there, but what you really need is in the box. And then really, that's all you need, right? Everything else we're going to say today follows from this, but we have to really think carefully about what we're doing, because we're going to also do area between curves and stuff here, in polar coordinates, and things get a little messy. You have to really keep this picture over here in mind. This is really what we're doing at all times. Lots of slivers, little triangles. All right. So, for example, let's find the area inside this card. The whole area, right? Later we'll just ask you to find the area of one petal or the area between these, right? But here we just want to find the area all inside of this. So again, you're going to have to think a little bit about what alpha and beta are, just like the discussion we had yesterday with linear, with the arc length, right? So one way or another, investigating with your calculator, maybe just know, because you know what this graph, how this graph is produced, is our limits are 0 to 2 pi. And then I'm just plugging in all that stuff, right? It's this thing, r all squared, that you see inside here, right? So 1/2 the integral of r squared d theta is what we're looking for. Yeah. Yeah, absolutely. We could do that in fact too. We could go from 0 to pi and then double it, right? On this one, does that answer your question? Or no? I don't want to say that. I don't know. I don't want to get in trouble or anything. Maybe. Think about that. I mean, what do you mean by symmetric? Because like we looked at the 3-petal rose curve. That's symmetric.
But that's not long. So
Yeah, but even if you were to rotate it and it was symmetric about x, you'd still have to only go from 0 to pi on it. It'd be easy to rotate it so that happens. Right? Take the graph of sine of cosine 3 theta, right? That has symmetry over the x-axis of the 3-petal rose curve. But so, yeah, I think the answer is no.
Okay.
All right, I had to get through though. And then feel free to do this on your calculator, as usual. Okay. This brings, actually, by the way, this brings to light something that I was talking with someone in the warm-up about. If you want to reference any function that you had in R1 or R2 or whatever in your calculator, you're not using Y1 or Y2. You're using, if you want to do this on the home screen like I did, you're going to pull up R1, which is still on the bars menu. You go to bars, function, to bars, Y bars, and then instead of function, you go to polar, and you can find R1 and R2 if you ever need them, right? Like you might now. So you might practice finding those features on your calculator and becoming comfortable with those. Yeah.
Is there a way of evaluating the integral by that?
Again, if you were, I have over on the board this crazy integral from yesterday, it might feel something like this, right? Because again, we have the suspicion that maybe there is a nice way to do it because we've got a 6 pi there. If time allows at the end of class, I will try to do that one by hand for you, right? But it is tricky and it involves probably some interesting trig stuff. I'm a big fan of the, yeah, we're going to get a 4 in there. That'll be easy to deal with. We'll get a 8 cosine theta, which we can deal with. The only thing that's weird in there is the cosine squared. There'll be a 4 cosine squared at the end, right? Every term of that integral you'll be able to do. But you'll need to deal with the cosine. You don't know how to integrate just plain old cosine squared, do you? Do you? No. No. Cosine squared, right? What's the integral of cosine squared? No one's told you that ever, but we can figure it out using the power reduction formulas as a trick. Yeah.
For most of the area ones or at the polar coordinates, will you be able to use a calculator?
A lot of the time, right? Yeah, I don't. The point is, I wouldn't expect you to do the things I just said necessarily. So, any questions on that? That's like straight up first example, just straight forward application of the formula I just gave you. Yeah. You ask such hard questions. I don't know. I mean, certainly, if you have access to your calculator, then there's no question in your mind you can do whatever you want, right? In fact, is there an integral? I don't think there is an integral feature on the calculator of anyone in polar coordinates. Is there? Anyone in polar coordinates? No, you can't integrate inside polar curves on your calculator. I was going to say you could see the picture, but at least you could trace. You could use the table, whatever, to get the picture that, oh yeah, this is 0, this is 2 pi. On this one in particular, you can investigate by plugging in some values too. You know when this is 0 and then when it's 0 again, right? You could actually solve for those two places, and you'll find that it's at 0, and then again at 2 pi, and again every multiple of 2 pi. So this one's a pretty easy one to say, yes, with definitive certainty we've done it right. But it is more complicated with ones that keep doubling back and like crazy stuff. So, we'll try to not be like too crazy too, right? We're trying to keep with somewhat tame things for the most part. We'll be really clear about what we want to say. Okay, so sometimes this is huge footnote on this, okay? Sometimes the area between curves is easy and is done like this, which is no surprise at all to you because it's like outer minus inner, right? It's just the one integral minus the other integral, right? I combine the two integrals together here, right? Neat. So let's do one that works this way, and then we'll consider the other case, the other multiple cases where that's not necessarily going to happen. All right, so here's my picture of this. We got two graphs here to figure out the area between. Let's be clear about what we're asking. Find the area that lies inside the circle, r equals 2. That's inside this guy. And outside the cardioid. So what region am I describing? Yeah, what would we call this? It's like the Batman logo area, right? Up top? I don't know what you call that. This like kind of that area in there, right? Yeah, it looks like the hair on the, right, so this is the hair on a small Lego guy or something. Okay, I don't know. Okay. All right, be nice, everybody. Okay. My hairline is receding like that too. So let's see if we can find the area of the hair. How do we do it? Well, let's just to be clear. Again, I always resort to the triangles every time, right? We have triangles on the outside here. Every single one of these. Let me zoom in on this just a little bit. Here's the curve. Okay, and when we're finding like one particular example of this, right? We have this inside curve which gives a sliver of triangular area like that, and then we have the outside curve which gives a sliver of triangular area like that, and the area we want is the area in between those two things for any given sliver, right? This area in here, right? So I think it's pretty clear, and that is the picture. That's a representative set of two triangles that is exactly the same picture we get all the way along this curve from, we should say, from what to what, theta. Yeah, if it's not clear, it is in fact from 0 to pi. Does it say that anywhere here? Let's just double check that that's true. How would we figure that out? Set them equal. We're actually solving a system of polar equations also here today, okay? So let's actually solve that. It's pretty clear maybe from our picture that that's true, but let's just verify that that's actually true. 2 equals 2 times 1 minus sine theta, and solve that equation. Ready, go. So we get sine, yeah, 1 equals 1 minus sine theta. So that 0 equals negative sine, or sine, doesn't matter. And then theta is equal to 0, pi, and a whole host of other things. But yes, 0 and pi. Okay, good. I think I'm clear now. Okay. Yeah. But again, finding the alpha and beta is maybe still some kind of a trick here for us. Okay. But once we're clear in that mind, and we have this picture up here in mind, which I think if you're having confusion about this, and you will start, this is not too bad, right? But they're going to show you some examples that I think will cause some confusion in your mind. Always go back to the triangles and show yourself, oh yeah, okay, outside in, okay, this makes sense to me. All right, so I think I'm ready to actually write this out here. I don't think I have it here, right? Yeah, okay. It's going to be 1/2 times, just what it says up there, from 0 to pi. And then, let's be clear about which is the outside and the inside, too, right? 2 is the outside, isn't it? 2 squared, I like that, minus 2 minus sine theta squared d theta. Okay. And again, just maybe hand that to your calculator. Okay? I don't mind. That's not. And in fact, even if we could do them by hand, that's kind of not the point anymore. Like that was the point back in December or whenever we were doing it, right? But like, getting this set up right is like the thing that's the very most important conceptual thing for us to do. Maybe there's a way to evaluate that by hand. That'd be cool. But, so I don't know what this is about. So here, I'll grab my calculator too. I don't know if you were helping me out here.
I got it.
Yeah, I wanna check you too. Yeah, so I'm getting about here. We'll do AP rounding here. I'm getting 4.858 approximately. But I could have easily typed it in wrong too, so I don't know. Okay. Someone else got that though. You got the same thing. Is that okay? Any question about how to do that first area between two curves, for example? Yeah, so like I said, this is a big footnote right here. Sometimes it's like this. Other times we have to be a little more careful. But this picture, doing the picture is going to save the day every time. Okay? Yeah.
Aren't you like, you're subtracting, aren't you like subtracting that lower area too?
So yeah, what are we actually subtracting? Like if we compute all the yellow areas, we've computed this area. So it's this thing minus this thing. Right?
But why is the second part just that part?
Yeah, so how would you compute the area of just this sliver? Well, you're going from 0 to pi. And if you add up all these yellow things, the first one looks like this, the next one looks like this.
So the bounds make it so like,
Yeah, the bounds limit it to be only that sliver there. So we did it. We're okay. Yeah. Sometimes it's more complicated, and that's like the only tip I have for you, okay? So let's try one and show you what we mean, okay? So here we're looking for the area, but shared by these two circles. Are you okay with the way we're explaining these? I mean, even if I didn't give you a picture, could you come up with it? If you have a calculator, say even, right? Okay. So here's r equals 1 down here. Oops, sorry. R equals 1 and r equals 2 sine theta, both of which are circles. And we'd like to find the area shared by both of them. Is it clear what we mean by that? What area are we describing here? You all right? Yes? You have a question? Yeah, are you guys good? Okay. What's the area shared by the two circles? What's this like football area right in the middle, right? Okay, so let's think really, really carefully about the picture here. Why is this more complicated? All right, I need to draw this down here because I'm already getting confused here. Right, so we got this kind of region I'm going to zoom in on here. Here's the pole. Okay, so now if I were to be honest with myself, and I'm sweeping through this area, right? Sweeping through this area, counterclockwise, as usual, then what do I encounter as I do this? Over here, as I'm here, I'm getting this contribution here, these areas here, do you see them? Which have nothing to do with this arc. Do you see it? All those yellow pieces have nothing at all to do with this arc. And then, as soon as I get to that mystery point, after that, these areas have nothing at all to do with this arc. Do you agree? Okay, and then we keep going, and I think that ends the discussion about how this is going to be complicated, right? You can keep going. Okay, do you see how this is going to work? And then when we get to here, we'll have yellow again. Now it's only contributions from this bottom arc and not from this one again, right? But we're using symmetry, so how about we just compute the area over here and double it, okay? Is that fair? It's the same. It's the same on left and right. So rather than break up this integral into 3 pieces, I'm just going to do this piece, and then double it, okay? But we have to do this really carefully. Is this going to be top function minus bottom function? Not at all, right? We're going to do completely 2 separate integrals that have different bounds completely, and then we'll just add them up. And it's not clear until you draw this picture that that's what's happening, okay? And it all happens, it hinges on what this, I'm running out of colors here. I guess I'll just use white. It hinges on what this theta value is right here, right? We're going to integrate from 0 to that value, and then we're going to integrate from that value up to pi over 2 on this other curve. Yeah, Nadia? Say it one more time. Why is the yellow? Yeah, so the yellow ones up here are triangles that when we sweep out a ray from the pole, hit this curve here, right? So those yellow ones are contributions from this function here. That's this one, right? So by yellow, let's be clear. By yellow, I mean this function. And by green, I mean this function, right? So let's do it here. We'll do the yellow one first. The area of the little yellow area is the integral, 1/2, the integral from 0 to, oh wait, we still need that theta value. What is it? Yes? Okay, good, we're ready now. Okay, so this was theta equals pi over 6. So we're going to integrate from 0 to pi over 6, just the yellow guy. Again, 1/2 that thing squared, right? D theta. And then we're going to add the green one, right? Which we're doing from, what are we doing? From pi over 6 on to pi over 2. That's a fun integral right there, just 1 squared. And we got 1/2 out front still, d theta. How does that look? And then we still have to, when we're all said and done, multiply by 2. How's that? You like that? And we can hammer this into our calculator now, but the fun part's over. Is this clear in our minds that we've just, and notice there's no like top function, bottom function, subtraction. And it's not seriously, it's not obvious until we actually like really think about it down here with this picture. I hope the picture makes it clear. Yeah, Emma. Run through the picture again. All right, so I'm zooming in on this region in red here. Is that okay? And as we sweep, so I want you to think about when we're integrating, if we're integrating in rectangular coordinates, kind of from left to right, sweeping like this, right? I want you to think about when we're integrating in polar coordinates as sweeping like this, counterclockwise around, right? So you could think about like sweeping a line, a ray from the pole, right? So as we do that through this area, what curve is that ray hitting? The answer is this one, right? Only. If we're talking about this red area. Until we get to pi over 6, and then that ray hits, if we're talking about this red area, hits this curve here. It also hits this other curve up here, but that's not the point we care about at this point, right? Is that clear? So in yellow, I'm representing the contributions from the yellow function, which is what what the areas we want to compute up until pi over 6. Is that okay? and then from pi over 6 to pi over 2, that ray coming out of the pole is always hitting only the green curve, and the yellow curve doesn't matter at all, right? Yeah, it is hard. So I don't know what this comes out to, but for the sake of time, I'm going to skip it. Right, there it is. Whatever that comes out to is the answer. Yeah, just tell it. You should get the same answer. Yeah, absolutely. Actually, that would be not too bad here. I think you can actually prefer for polar coordinates quite a bit, because the equations of these things are not super nice. You got some square roots in there, right? And but I think maybe you could still do it. I don't know. Okay, let's see if we can at least set up this. I know we're kind of running short on time here, which does another minute here. Let's see if we can point you in the right direction on this guy, and then we'll call it a day here. Okay, find the area inside the 4-petaled rose curve and outside the circle. Wait. Okay, I got the picture in front of me too, and I'm still struggling. Okay. Inside the petal, the tip, and outside the circle. So all, yeah. Okay, so now I'm with you now. All right, so we got all these areas out here. It's pretty clear to me, even though the picture up here is not very symmetric, that all we have to do is find one of them. In fact, actually, we don't even have to find one if we want. We could find half of one, right? If we wanted to multiply by 8. It doesn't matter, though. So we're going to need to get those intersections, aren't we? Or at least one of them would be even sufficient. And then there we can do outside minus inside, can't we? So here we actually will do that outside minus inside. So be very careful of drawing pictures. So sorry we didn't get to finish this example, but I think you've got at least the big major points here to get you going on the last one.
The school store will be open today during lunch. Will the following students please come to the main office? Kayla Aza, Christina Lou, Angel Ramos, Jack Ramos, Max Agbula, Frank Mose, Marcelo Molina, Elva Joya. Please come to the main office.
Yeah, the grade's on the headline. Do you guys not see your fourth quarter headline grade?
I don't think the fourth quarter.
You only see your third quarter grade? Yeah, they weren't. I thought maybe you guys.
Oh, you mean the unit test?
Yeah, I just want to know.
Yeah, I mean, I put it up a couple days ago. Actually, I had it done over the weekend, last weekend.
I think it's because
Claudia Espinosa, please report to the registrar's office.
Yeah, I know for a while. I was wondering why people hadn't come to me in tears yet. I mean, no, it's not that bad.
you like, you're giving me a hard time.
I can tell you. Yeah, oh yeah, tell your friends. I do have it. Right. I thought it was on headline for a while here, and I do need to give them back.
No,
You're so strange.
fourth quarter is not yet.
I'm straight. I don't know if these are nice.
Don't be scared.
I hope it's actually.
If I start off the quarter,
If I start off the quarter badly, it's
Oh,
gonna
no.
be, I'm gonna win it on the.
Here's one for you, Natalia. You can look at it, but give it back to me, please, of course.
Also, Ms. Kular's English 9A High School Plus class is
think all the
canceled
present
for
company did
today.
fine.
It will resume the Tuesday after break.
Let's hear it. See, you did.
was it ours?
Yeah, you did fine. Yeah.
Oh, okay.
God.
Oh.
Yeah, you're like half of the population they got.
Shoot, I read
The one unit test that people fail, I do well, and the one people do well, I fail.
I know, like I said, seriously, as long as you're with me and you understand stuff, I mean, right? It's not bad. It's really not bad.
Oh, it was just, oh, wait,
This is
it
actually
was
waiting for
just
me.
easier than
Yes.
last week. I forgot to square the 4. Oh my gosh.
So good job to all of you, actually. Yeah, good job.
But
See you
is
guys.
it? Okay, bye.
Yeah, you have a spell some breaks. What that previous one was, or which one we're just doing? Yeah, let me go to you. Mikhail, you mean the test? The reason? Test, right? Yes, okay. Sorry, hold on. I had some fire. And then I will compute this. Actually, I probably have my notes. You have a calculator? You want to clear it? There's one small correction to make on there. It's pretty obvious that it needs to be corrected, but I need to highlight it for you. Cool. And then there's, so on problem 6, part A, number 2, it says 15.4. It should say 14.4. It's pretty clear. Just fix it right now, though. This last example,
Yeah.
approximately 15.306.
Okay.
Is that what you got?
Yeah. Okay, thank you, sorry. Have a nice spring break.
Yeah, likewise. You're taking the test too right now, Kyle?
Yeah.
Is that what we're doing? Sorry, to keep track of all my
That's cool.
children here.
Hopefully it's not too hard.
It's pretty painful, but you know. All right, I'm just gonna leave it.
Oh, okay. Thank you.
Have fun.